Can everybody see the screen okay, or do I need to turn off any lights or anything like that to increase visibility? We're going to talk about is the concepts of self and mutual inductance. Self-inductance should largely be a review. So you guys have all had Physics 202 by this point. I believe you were required to have it by this point. Will generate a magnetic field, right? A little picture here of a portion Y connected to some greater circuit. I indicate that the current flowing through the wire, I of t, some time varying current, flowing from left to right through the wire. What is the magnetic field going to look like for this wire? So I see somebody trying to use the right hand rule, so that's absolutely right. Magnetic field. So I'm going to do the magnetic in this kind of light blue color. So we should see that for the field, like a circle with a dot in the middle of it to be like the head of the arrow coming out at you, but for whatever reason, the dots are not showing up in the center. There we go. And then below the wire, currents flowing into, or excuse me, field lines flowing into the page. Well, Terrence, are you okay back there? Can I find here? I don't know. There's a seat up. So these field lines, we're going to you might have also just heard it called the magnetic field. To me, magnetic field is H, magnetic flux density is B. Okay. So the units of our magnetic to 1 Web per meter squared. And a Web meter squared. Those are our units for our magnetic field, or magnetic flux density. Okay. So what happens if we, instead of having a long straight section of wire, what happens if we coil the wire up around some sort of cylindrical form? We wind up getting a solenoidal coil, right? We talked about these way back in Engineering 221. So I'm going to draw a core here, and I'm going to assume a cylindrical core. Like so. And I am going to wrap a wire around this core. Forming a coil. Let's say that this core I of t will be flowing into that top terminal, flowing out of the bottom terminal for what it's worth. Let's say that this coil has n number of turns. And should be for this configuration. Right, so in a solenoidal coil, if our fingers wrap around in the direction of current flow, our thumb gives us the direction of our field lines, right? So if our fingers are curling around like this, our field line should be directed out. Absolutely right. So here directly we should have something like this, but as we get a little bit further away from that axis, that radial axis of symmetry, we should see that the magnetic field lines start to wrap back around to connect to each other, because magnetic field lines have to form closed loops. There is no such thing that we know of yet that would be considered a magnetic monopole. So everything has to wrap back around to form a magnetic dipole. So we're going to see something like this. These lines wrap back around. Like so, we're going to see the same thing on the other side. Sorry for my inability to draw. Magnetic flux that is passing through this coil is defined as the product of the magnetic flux density area of the coil, which we'll call A. So our flux phi B will be simply B of T times A, where A is the vector. You should know that the real definition for magnetic flux would be the integral of B dotted into some different particular configuration. The is in the up direction. The field lines are also in the up direction. So because they're in parallel, we just get B times A. Okay. The unit of our magnetic flux is the Weber, where once again, 1 Weber is a volt second. And we can define the flux linkage of the coil, which is going to be lambda. Trying to remember my Greek alphabet here. Our flux phi B, our flux linkage is once again measured in Webers because it's of the flux that was measured in Webers. Okay. For a linear system, meaning that if we don't allow the size of this coil to change over time, where our flux linkage lambda is equal to L, our self-inductance, times I of T. And then using Faraday's law of electromagnetic induction, we can induce a voltage drop across this coil, call that our voltage V of T. And V of T is defined to be the derivative of the flux. This is going to look like the derivative of L times I of t, which looks like L di way back in circuits 1 and used over and over and over again throughout the duration of circuits 2. Mutual inductance may not necessarily be revealed. So we have a coil like this generating some amount of flux, and that flux is able to leave the top of our coil and circle back around to the bottom of our coil. So if we had a system where we had some sort connected to a coil, I'll draw my coil over here. Like so. And let's define my direction of current flow. Our primary coil having N1. This is going to be our voltage V1 of t like so. And then let's put over here secondary coil. And this secondary coil has N2 turns, and I'm going to open circuit it. So if I'm passing a current through coil, I should see flux lines like so. I'm going to call this flux phi 11. So this is the magnetic flux of magnetic flux that will coupling to the second coil, right? Phi 12. So it is the flux produced by current 1 passing through coil number 2. Let me write those flux definitions down there really quickly. So phi 11 is the flux produced by coil number 1. Coil number 1 is the flux produced. It's looking more terrible than I will allow. So since there is a magnetic flux passing through coil number 2, because the current I1 is changing in time, what we should observe is an induced voltage drop across, right? So we should see some voltage V2 as a function is the derivative of the flux linkage of coil 2 with respect to time, where flux linkage is simply the number of turns times the flux, right? So that means that we're going to have the derivative with respect to time of N2 times phi 1, 2. Well, phi 1, 2 using these relationships and rearranging to solve for the N number of turns of coil 1 multiplied by the current flowing through coil 1. So that's going to look like L1, that was right, divided by N1 times expression down here, so I'm running out of room. N2, N1, and L1 are all constants. So we can take them outside of our derivative. So of I1 with respect to time. And we're going to call this M21 I1 by dt, where this M21 inductance of coil 2 induced by the current I1 of t. What would happen if we moved our excitation source from being connected to coil 1 over to being connected to coil 2? Going from right to left instead of left to right. Okay. So in that particular instant, so let me write this down. Coil number 1 and coil number 2, we would get a voltage by dt, and we would wind up getting an induced voltage of V1 would be d the exact same as we have above. We'd have N1 over N2 times L2 times the derivative of I2 with respect to time, which would be M12 the I2 by dt. So our last thing to observe here is that energy is conserved in this system. What should the relationship between M12 and M21 be? They have to be the same thing. Right? So generally speaking, we are going to have M12 is equal to M21 is equal to just M, the mutual inductance observed between two coils. What happens if we excite both coils? So if we have a system like so, where we have some sort of time varying excitation and over here we have some coil 2. By a time variable. Let's define our current I1 to be flowing this way. Let's say is flowing in this direction. I'm going to define the positive polarity terminal of my induced voltage V1 on top, and I will define the positive polarity terminal of my induced voltage, V2 on top as well. What we should wind up having is some flux phi11, some flux shared between our coils that I'm simply going. For a system like this, we have a flux linkage phi1 that is equal to L1 times I2 of t, and we have a flux linkage lambda 2 that's going to be can't believe you guys are yawning. This is fascinating stuff. L2 times I2 of t. We can determine our induced voltages, right? So our voltage V1 of t is the derivative of flux linkage 1 with respect to time, which is going to look like L1 di1 by dt plus m d2 will be the derivative of flux linkage 2 with respect to time, which is going to look like L2 di2 plus m times the derivative of I1 with respect to time. All right. So the next thing that I am going to talk about is going to be the dot convention. This much detail is cumbersome. Okay. Now the question kind of you know that the 30-ish minutes that left in class is actually enough time to cover this material, and it can be. Would anybody be opposed to ending class about half an hour early today and picking this up on Monday, or do you want me to keep on trucking? Because I've got notes and examples, but it's entirely up to you.
I'm good to wait Monday.
I figured as much. I don't want to waste anybody's time, but I also don't want to get halfway through something. I'll see you all on Monday, and like I said, I'll try to get the tentative course schedule and all that kind of stuff wrapped up, and I might put up your first homework assignment over the weekend as well, which you probably won't be able to do anything on it yet because we haven't covered the dot convention, but at least it'll be there.